I don't know if I pronounced that correctly. They lay out how these loops push already popular artists forward while making it harder for lesser known artists to be discovered. Several studies emphasize that giving us users more agency, such as adjustable controls or transparency into how rankings work, can reduce the bias and improve perceived fairness. Porcaro et al. And Bauer and Dennison highlight user-centered design as a key mechanism. Other work by Dejdu and Gupta argues that fairness isn't something you bolt on afterward. It depends on the goals of the system, the quality of the metadata, and how discovery and satisfaction are balanced. Together, this literature shaped my project, a prototype that's both technically transparent and explicitly designed to give users control over the popularity discovery trade-off. This project uses both technical and ethical methods. Since Spotify's internal algorithms aren't accessible, I analyzed the public metadata available to their API. This offered genres, popularity scores, and related artists to understand how bias emerges. Then I built a full stack prototype using React and Node and Express. The core feature is a slider that lets us users shift between mainstream and low popularity recommendations. The goal is to test whether transparency and user control can meaningfully rebalance exposure. The system is structured as a modular full-stack app. The React frontend handles user input, while the Node Express backend communicates with the Spotify API and competes similarly in discovery scores. I designed a transparent scoring model that uses a lambda parameter, which I call the slider coefficient, to balance genre similarity with discovery. Artist data is normalized to ensure consistent scoring. This structure sets up a future step the database layer can log runs or store cleaned metadata. I focused first on getting a reliable backend MVP. All endpoints were tested through Postman and curl, and I implemented token caching to avoid unnecessary Spotify calls. The candidates by genre endpoint is where the scoring model lives, combining genre similarity with discovery weighting. I structured development around a Trello Kanban board to keep tasks incremental and visible. Front-end integration is the next step now that the backend pipeline is stable. And this is what I ended up having as a file structure for my application. So you can see the backend and also the front end here. I did manage to have a database connection with Mongoose and MongoDB, but that's a future work process for, I essentially want to save some items there to the database, but that's not currently working. This is what the initial prototype looks like. There's a search here. So you search for any artist that you type in. And then with the slider, you can, select from score from 0 to 1, which is, I guess, 100%, depending on how much, how much popular or how much more discovery you're looking for. This is just an example of one artist and how, I guess, the output changes. In the left-hand side, I had an artist called Bjork. I decided to put, the 0% popularity score, and the top recommendations are, genres that are not really well known, like art pop, art music, art pepper. I mean, I don't recognize any of these, and artists like Trip Lee and Artie, I've never heard of before. But then when you change it to more discovery, or you change the slider all the way up, then you get people who are familiar, like Lady Gaga. Maybe some of these are not familiar to you, but I recognize Massive Attack and Tricky and Portishead, etc. And this is the Kanban style board that I created in Trello, just with a few simple columns, the to do, in progress, testing, and done. And some of these labels, for example, the green represented back end, um, the blue is front end, the purple is more like I guess for discovery type stuff, and yellow was supposed to be testing and documentation. For data collection, I used only public metadata, as I said before, from the Spotify Web API. This includes genres, popularity scores, followers, and related artist networks. Because no personal or behavioral data is involved, the project stays IRB exempt and privacy safe. Early testing using memory objects and small JSON files. And the system is structured to move to MongoDB when I integrate persistence. In analyzing the data, I looked at the metadata completeness, especially genres and popularity scores. I compared artist popularity values with their real-world cultural visibility and examined how the slider changed ranking outcomes for different seed artists. I also compared public API outputs with curated playlists to see what Spotify's internal systems might be doing differently. There were three main findings that I came across. First, Spotify's popularity score doesn't always reflect cultural impact. Like some niche artists and global superstars return surprisingly similar values because their metric is engagement based. As an example, I think Bjork had a popularity of like 88%, and Lady Gaga had a popularity of like 92% or something like that. But I know Lady Gaga is more mainstream and Bjork isn't as mainstream, so that's an example. Second, missing genres create fairness issues because the model can't compute similarity at all, which means it affects the small and emerging artists. And third, the slider worked exactly as intended, so pushing the lambda toward discovery consistently elevated lower popularity artists into the recommendation set. The conclusion now. In this project, I started with a single observation, which is engagement-driven recommendation systems like Spotify's. What's that? Oh,
Sorry, please continue.
I think
okay. So I was saying, yeah, this is the conclusion. So Spotify's algorithms tend to push what's already popular and hide the emerging niche artists. Prior work calls this popularity bias and shows that it's not just a technical issue, but also a fairness and cultural equity problem. Because Spotify's internal recommendation engine is a black box, I focus on what is available, like the public metadata that I mentioned before. Using that, I built a transparent scoring model where genre similarity is the G, discovery is D, derived from 1 minus popularity over 100, and I slider parameter as lambda, which I also call the slider coefficient. Testing the prototype confirmed patterns described in the literature. Like I mentioned, the first artists were with very different cultural footprints, like Bjork and Lady Gaga, returned similar scores. Secondly, missing is or incomplete genre data. They turned out to be a major fairness issue. When an artist genre array is empty, the model can't compute genre similarity, which means fewer or no recommendations at all. Despite these limitations, the slider did exactly what it was supposed to do. When set toward discovery, lower popularity artists moved up in the rankings. And when set towards similarity, the system leaned back towards mainstream, well-tagged artists. For the future work, I would like to, as I mentioned here, continue with adding CRUD and MongoDB for saving the analyses for sessions. And I would also integrate a different API. The only ones that actually have data available to the public are the Spotify API, the Tidal API for Tidal Music, And I believe Deezer also has an open API, but they're limiting how many people can have access to it at a time. And all the other ones you have to pay for, like Apple Music or just any other music platform, pretty much. And for expanding fairness metrics, I would do that. On top of that, I like to bring in more explicit fairness metrics like popularity distribution, like before and after the slider, and etc. And these are some of the references that I used. I did have a lot more in my paper, about 15 or so, but these are the ones I've mentioned here. Okay, any questions?
Then you
Yeah.
have,
Sorry, no, go ahead. If you have a question, I'll let you go first.
I'm just asking if anyone has any questions.
I do have a question. So let me see. Do you see, hold on one second, just want to make sure I have that question. If you had more time and resources, what would be the next feature you'd add to this prototype?
The next feature certainly would be the MongoDB and CRUD backend. Because right now, as I said, you can do a search for artists and it gives you an output JSON that it's, rendered in React, but you can't save your data right now. So that would help a lot. So you can, compare different analysis there.
Thank you. And my follow-up question to that was, how might your work contribute to the broader conversation about algorithmic accountability and AI systems?
Well, I think, this is the first time I actually really looked into this topic, and it really did kind of reinforce what I was fearing, which is, not many people have open data, so you can't see any of their algorithms. I mean, I guess it's kind of obvious it's for monetary reasons. But yeah, unfortunately, I think there's a lot of papers on this. I think if I had much more time, rather than just do the CRUD API, I probably would try to incorporate some sort of like machine learning, like ML type approach to see how these algorithms actually work. But yeah, I don't know yet how I would actually influence the. But thanks for asking.
Okay, thank you.
Thank you, everyone. Should I stop sharing my screen? Let's see.
Thank you, Jocelyn.
Thank you.
So next we have is Emmanuel. Are you there?
Oh, yes, I'm here.
Yeah. So
Are
you
you
will have
hearing me?
20 minutes for the session,
Okay.
15 minutes for your presentation, and rest for the Q&A. So you can start now.
Okay, I'll be sharing my screen very soon. Sorry guys, I'm trying to share the whole screen, but for some reason it's not working. Okay, so is everyone seeing my screen? Just want to
Yeah.
make sure. Okay, is it good enough?
Yeah, it's the PPT.
Okay, so hello everyone. My name is Emmanuel Kensese. Today I will walk you through my AI-driven hazardous waste management prototype. The goal is to improve waste classification, environmental monitoring, and prediction using lightweight, practical AI tools built for real warehouse conditions. Here, here I will move to the presentation. Sorry. We will start with the problem statement, motivation, background, related work. Then we'll move to approach, design, implementation, data collection, data analysis, findings, conclusion, and then we're going to finish with future work, key references, and Q&A. So let's begin with the core challenge. Warehouse still rely on manual waste identification, which leads to misclassification, safety risk, and compliance issues. Workers may make quick decisions without chemical training. This project introduced a lightweight AI tool to support safer and more consistent decision. Now, why we know the problem, here's why it matters. In my 5 years as a hazardous waste coordinators working at Amazon, show me how common these mistakes are in fast-paced environment. People are moving, multitasking, and often unsure about hazard level. I wanted to build a system that supports them without requiring specialized expertise. To see the bigger picture, here's the background. Waste handling still relies on visual checks, paperwork. There's almost no real-time monitoring. As warehouse operation grow, the lack of automation leads to delays, inconsistencies, and safety concern. So what does research show? Uh, recent research shows strong progress. CNNs reach high classification accuracy. High spectral imaging enables non-contact detection, and IoT sensors support real-time tracking. But many solutions require perfect data set or expensive hardware and usually focus only on one part of the problem. Now let's look at the remaining gap. Studies highlight several challenges, such as a limited data set, transparency gaps, environmental consideration, and also predictive analytics shows potential, but often apply only in narrow scenarios. So the path forward is to build an AI system that are adaptable, expandable, and sustainable. With those in mind, here's my approach. My solution combines three components: a CNN for classification, a simulated IoT monitoring system and forecasting ready architecture. The goal is safety, transparency, and human oversight. Next, let's see how the pieces fit together. This diagram shows how workflow classification and monitoring and forecasting operate as a modular component. Each part support the others, creating a scalable and explainable system. So now let's walk through how I build it. Implementation. So the implementation follow a phase build, training, and evaluating the CNN, simulating the IoT values, and preparing the system for the XAI and audit logging. Each step ensure the prototype remains stable and testable. So now let's look at the data behind it. Data. So I use a open source image from Kaggle and generating synthetic sensor data representing temperature, VOC, and bill fill levels. Image were labeled, prepared for training, and synthetic values simulated realistic warehouse environments. No human data was collected, so the IRB approval wasn't needed. And here's how the data was prepared. So images were resized, normalized, and split into training and validation sets. The sensor data was stored in CSV files. Everything was version controlled to GitHub to keep the workflow organized and traceable. Now let's look at what the data reveal. So the data reveal the model performed well on clean, well-lit images, but it struggled with poor lighting, occlusion, and damage labels, condition common in real facilities, per se. So the IoT data help validate the threshold alerts, and the forecasting test confirm that the architecture is ready for predictive expansion. Here's what the prototype proved. So the prototype proved that CNN consistently distinguished hazardous from non-hazardous. Most predictions were high confidence, and low confidence ones were correctly flagged and for human review, supporting a safe human in the loop approach. And the IoT simulation generated temperature, VOC, and bill fill alerts, and the system successfully supported basic forecasting. Overall, the prototype functioned as a stable, lightweight decision support tool. Here's the conclusion. Here's the final outcome of the project. So, the decision addressed, the system addressed the original problem by improving classification accuracy, adding real-time monitoring behavior. Although it used a small data set and synthetic sensors, the prototype provides a solid foundation for real-world deployment. And finally, here's what comes next. So for future work includes integrating real IoT hardware, since we only use simulated one, expanding the dataset with real warehouse images, and adding explainability tools like GradCam or SHAP, and eventually automating compliance reporting. So these steps will move the system toward full production use. That's what I believe. And then, so before we actually, next is references and then question. So, but before we move to question, I would like to share actually the prototype itself. I hope it works. I believe it might take some time since it's like 1 minute and 30 seconds long.
Presentation done?
Yeah, it's still loading. It's like halfway. Let's hope.
Okay.
Yeah. So I'm actually loading the demo code.
Oh, okay.
Yeah. Then after that, we can move to questions. Okay, looks like it's taking its time, so we can actually, oh, there, yeah. We can actually move to questions because I think it was taking too long and then just stopped.
Anyone has any questions?
I did
Sure.
have oh, sorry, go ahead. You can ask a question, Jocelyn.
Okay, thank you. I was gonna ask, it's really interesting that you're gonna incorporate like Internet of Things, so IoT type stuff. What do you think you'll do with that? Like maybe like I mean, what kind of IoT are you gonna implement?
So the primary goal was to actually implement the one with a wheel sensor to actually, if for example you have a bin of hazardous material, it can sense it and will let you know the level of actually how hazardous it is. But yeah, I found it tricky, and then in 10 weeks you can't do that. So I just did a simulated one where it just will show on the screen like, hey, this is the level hazardous, and it gives you the temperature and everything. That was kind of the goal because of where I work. So then it's just that the person actually can have an idea of how hazardous whatever is inside of that bin. So he can actually, move with precautions. Because most of the time you don't know, it's when you open it that you would know what it is or what's the level of hazardous it is.
Okay. So were you thinking of using something like Arduino or Raspberry Pi or something like that, or something different?
No, so to be honest, I really didn't go that deep because I just realized it was going to be too much. So I kind of just stopped to the simulated one where I just, use the app because I use the crowd platform app to actually show everything. That's why I was trying to upload here, but for some reason it just took too long and then it didn't work. And then you guys will have at least have a visualization of what was happening. But unfortunately, it didn't go to.
Oh, okay. Well, thank you.
All right.
My question would be, what's the estimated cost, or what do you think the estimated cost would be to implement your system in a single warehouse?
Can you repeat the question?
Your system, the one that you were gonna to demo,
Yeah.
what do you think the estimated cost might be to implement that system in a single warehouse?
Hmm. I mean, I, it depends. I think it will depend on the company. If the company is ready to spend, I'm pretty sure they might spend as much as possible. But I don't think it will be really expensive, because I think it's probably maybe having real life sensors that could cost, but I think everything else will work with AI, so I don't think it will be too much, but it could be expensive, depending
So,
on.
okay. Okay.
Yeah.
And you mentioned, AI. My follow-up question to that would be is if a worker disagreed with the AI classification, um, you know, how would you balance the AI recommendations with expertise? I guess if someone disagrees with the AI classification, what would be the process that they would have to go to, or you recommend that they would go through? And then how would you balance the AI recommendations with the human expertise
Yeah,
in that
so
area?
yeah, regarding that, we still using the human in the loop approach, which means that uh, the human is still going to be an active participant in the decision making. So if actually the decision comes as incorrect, then they actually can send the feedback and that will be corrected. So, which means through, I think because programming and programmation is never perfect, there's always a loop. So that's why human expertise is still necessary, because if there is something that actually is wrong, or something, or that, let's say that the program read wrong, then we actually can get the feedback and fix it. So
Okay,
we will still work with people that actually have high knowledge situation to also get their confirmation that this is actually true.
got it. Okay, thank you.
Right. Any more question? And one last time, sorry for not being able to upload the prototype. Seems like it's too, the size is too big, so it didn't go through. Thank you guys. That will be it.
Thank you, Manuel. Now it's Vidya Lakshmi. Are you there?
Yeah, yeah,
Yeah,
I'm
so
ready to share the screen.
yeah, you can start. You will have 20 minutes in total, 15 to do your presentation and 5 for Q&A. You can share your screen now.
Can you able to see my presentation?
Yes.
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 But I couldn't able to see. Are you seeing the home screen or the PPT slides?
Yeah, I think you are only sharing the slides.
I'm sharing the slides.
Yes, it's only the slides. It's your PowerPoint win tab. Yeah. Now it's good.
One second. Yeah. Is there an option for starting the presentation slide? Sorry, this is the first time I'm presenting online, so I'm not sure about the option. Because I'm seeing the notes beside the slides. Is there any way to, or is this okay?
Yeah, it's only the slides now.
What?
Yeah, it's the slides. The slides are sharing,
You can able to see the
not
slide?
the entire window.
Yes, we can see your slides. We not seeing your notes, so you're good.
Okay, thank you. Good afternoon. My name is Vidya. Today I'm presenting my independent research on creating AI agents that can manage water distribution networks during critical drought scenarios. We are facing crisis where traditional static control systems can no longer handle the unpredictable nature of modern climate patterns. We need systems that adapt. The current AI research focuses on optimization, saving energy on a normal day. My research focuses on survival, preventing system collapse during a 1 in 100-year drought. To solve brittleness, I propose a new framework called MPCL MAPPO. So here it combines the state-of-the-art policy optimization with a structured curriculum that teaches agents how to survive. Here I developed a custom simulation environment that models the nonlinear dynamics of a reservoir and two urban demand zones. To ensure the benchmarks are realistic, I injected a real-world 2023 precipitation data into the simulation. This forces the agent to react to actual weather patterns, not just random noise. So here is the snapshot of the environment class. The system is designed as a partially observable Markov decision process where agents must make decisions based on local data and peer communication. I utilized a CTDE architecture. During training, central brain guides the agents, but during execution, the brain is removed, allowing the agents to operate independently on lightweight edge devices. So this is the neural network design, which I designed. So it decides how to move the wall and what to say to the other agents at the exact same time. So here you can find the snapshot of my training. We have phase 1 and phase 2. Phase 1 is under normal condition, phase 2 on drought condition. So we can say the agents are forced to adapt. The logs shows that the transition happens. This is where the resilience is learned. The numbers speak for themselves. The standard AI failed over 1,800 times. My curriculum trained model reduced those failures to just 50. This is a 97% reduction in critical infrastructure risk. So this graph explains the why. The agent learned to voluntarily throttle supply, underserving demand slightly today to ensure the reservoir doesn't run dry tomorrow. The green line is the supply line and the blue is the demand. So we can see how the agent learned to underserve demand slightly so that the reservoir doesn't dry. I also tested removing the communication channel. The system immediately destabilized due to resource racing, proving that communication is non-negotiable for safety. Finally, I tested the model on completely unseen data from 2023. It maintained its high performance, proving it can generalize to real-world weather patterns it hasn't seen before. So in summary, this work proves that we can quantify resilience. We reduced system failures by over 97%. More importantly, we identified that explicit communication is not optional. It is mathematical necessity to prevent the resource racing. Moving forward, I plan to bridge the simulation to real gap. So my next phase involves integrating the real SCADA sensor data to create a digital twin. And I also plan to transition to graph neural network, which will allow this policy to scale from a single neighborhood to an entire city water grid. I would like to share that this paper is under review in Water Resource Management System by Springer. And also a preprint of this is deposited in SSRN by Elsevier, which is an older version. But this one is a updated version where I have conducted rigorous testing against the baseline models for the ablation study. Thank you. Now I'm ready to take questions.
Hi, I do have a question. This was outstanding. When you were saying this, I was thinking how useful this would be for critical infrastructure for some of the water systems that are in or around the area. My question would be is how long do you think it would possibly take for the AI to learn the system enough to be able to throttle effectively? Because there's going to be, I'm assuming there's going to be a learning curve for the AI model.
Yeah, so through an ablation study, what I learned is what it proved is it is not about the training time, but it's about the structure of the training data, which is specifically the curriculum learning, which I introduced that curriculum learning into the training. It slowly made the agent to experience the normal condition, from normal condition to the drought. So it learned, like, it is not heavily penalized. So it stabilized slowly. So it's all about the structure of the training data. It's not about the training time.
Okay. Sorry, go ahead. Okay. I thought that was so it's about the structure of the data that's presented to
Yeah.
it. There's still when you were doing it, because I'm assuming this happened over a period of time when you were doing this information and or this data. You were using structured data. Do you have an estimate of how long? Because you said it happened slowly, which is okay. Was it like an average of 3 to 6 months with that structured data, or while you was working through it, or a little bit longer, hypothetically?
Yeah, so I was working for 6 months to structure the data, to expose the model to that structured data, to design the curriculum, learning, the policy brittleness, everything. So it took 6 months, yes. But the training time
Mm-hmm.
for the model, it took like 1.5 days. I tell you why, because I was using a TPU
Okay.
from Google Colab. So it's not so efficient. I didn't pay much for it. I just paid $10 and took some computing power. And I was training for 1.5 days. Yeah.
Okay, and that's just one thing. I mean, because when you're looking at it, and so a company is looking to go ahead and potentially take this on, right? You've identified areas of flight risk, meaning that these things need to communicate. They need communication, or they'll enter into survival mode. Correct me if I'm wrong. Which is great to know that the learning path and the learning trajectory as you go along with this, that may be good to possibly have in your back pocket as you're developing this. If you continue to develop this, is an estimate of roughly how long do we think it might take the AI or the agent to synthesize that data to normalize within maybe a set environment or a specific environment. There's no concrete. It'll take 12 months to do it because CPU or any of the other water treatment places, each place has their own. Will probably have their own, but to have an idea as you're going through, even if it's a small one, for your case study, it may be helpful to have in your back pocket as you go. I'm assuming you're going to present this in to some more areas or whatnot. But good, it's great work.
Yeah, thank you. Thank you so much. Any other questions?
Oh yeah, I just have one question. So, what was the biggest challenge you faced while building this project?
So when I was framing the curriculum learning for the model, so I started with a baseline model, and I was thinking how to make this model to reduce the failure, because all the baseline model in the market is achieving like it failed over 1,800 times than what I have developed now. So I wanted to frame a curriculum learning, and it took little time for framing that, for making myself to familiarize with the policy gradients and how to stabilize the variance, all those things. Yeah, the curriculum structure part, it took more time.
Oh, okay. And just one last thing. So, if you had a chance to redo this project again, let's say, what would have you done differently this time?
So yeah, I'm gonna make it like more complex. I'm going to introduce more complexity into the system. Currently, I'm testing with the one reservoir with two urban demand zones. So if you give me an opportunity, like if I had a chance, I have a chance to improvise this project, I'm going to think of the complexity. How can I scale across the city-wise?
Oh, okay.
Any other questions? Okay. Thank you, Vidya Lakshmi.
Thank you. Thank you so much.
Thank you everyone for the project. This was a great presentation from all of you. Yeah.
Thank you. Good job, everyone.
Mm.
Great work, everyone.
Thank you. And bye, everyone.
Yeah.
Thank you.